Hello students, in continuation of the Galois mathematics, we will continue further the same thing in this module. We have already learned the definition and the properties of set, a group, a ring and a field. Today our discussion will be mainly concentrating on the polynomials. Polynomials, let R be an arbitrary ring. The polynomials over this ring will be given by the expression written here. F x equal to summation of the i's going from 0 to n a I into x I, where all the a i's are the coefficients, and the coefficients based on the value of the I, a I is moving from a 0 to a n. Remember, this n is a non-negative integer, and x is not a part of this ring. X is called the interdeterminant, and it is introduced for the convenience in mathematics. In particular, this expression of this polynomial can be specifically written like this, where the first equation is derived from the next by deleting all the 0th coefficient elements. And with the 0th coefficient elements, actually your higher order, the maximum order of the x actually is going up to n plus h, where h is another positive integer. However, as 0th coefficient terms can be discarded, the polynomial expression that we will deal in this module will be given by this form. When comparing two polynomials, suppose f x and g x are the two polynomials over this R, and let us also assume that both of them are having the power of x equal to n. So, both of them are having maximum power that is associated with both of them is equal to n. So, the polynomials can be written like this: f x is equal to a I x to the power I, g x is also b I x to the power I. So, under what condition we can say both the polynomials are equal? The condition is if and only if a I is equal to b I. As the numbers higher order number is going up to n, hence this is the sufficient situation. And if it is not, I mean f x is going say up to the order of n 1 and g x is going up to the n 2, then for the polynomials to be equal, definitely you have to also prove that n 1 is equal to n 2. The sum of the polynomials f x and g x, when both of them are having the same power of x equal to n, then it will be given simply by a I plus b I to x I. Remember, if they are having different values of n, then it will be the summation will go up to maximum of n 1 comma n 2. Anybody maximum of n 1 comma n 2 means that whoever is having the higher value, the summation will run up to that. To define the product of two polynomials, say we will start with the same, having considering that both are having the same structure, and if they are having the same structure, it will be n plus n, and if it is having the up to the value of m, g x is running, then it will be given by n plus m. So, if it is n 1 n 2, then it will go up to n 1 plus n 2, where actually this a I and b j, they will be combined in the form of c k, where c k can be expressed like this. So, there is a relation of a I, b I and c k given by this expression, and the product is given by this final expression f x g x is equal to like this. So, it is easily seen that with this operation, the set of the polynomials over R, they also form a ring. So, polynomials are a part of a ring, and the set of the polynomials who are having such kind of the properties, they can form another ring, which we will call the polynomial ring over the ring R. So, the ring that is formed over the by the polynomials over R with these above properties will be explained like will be expressed by R x, whereas the R x will be given as I going from 0 to n a I x I, where a I is drawn from the ring R and n should be a positive and positive integer greater than equal to 0. If if the 0 element of this ring is a polynomial for which all the coefficients are 0. So, the all coefficients equal to 0 polynomial will be called the 0 element, and polynomial will be called also the 0 polynomial. Now, definition, next definition. Suppose this is a polynomial a I x I summation going from I equal to 0 to n over the ring R is a polynomial. And we also consider that it is not a 0 polynomial. So, we can think that if it is not a 0 polynomial, so none of the coefficients are 0 and hence a n is not equal to 0. Then this a n will be called the leading coefficient and a 0 will be called the constant term. The n will be called up to which the summation is running. This n is called the degree of the polynomial, and hence we can write it like this. By convention we set that degree 0 is equal to minus infinity, and all the polynomials who will have the degree less than equal to 0, which we will call them the constant polynomials. If the coefficient of f x of all the polynomial coefficients are equal to 1, we will call them the monic polynomial. So, see, there were last slide we have learnt about the 0 polynomial, where all the coefficients are 0. All the coefficients are equal to 1 means a monic polynomial, and if the degree is less than equal to 0, polynomial will be called as a constant polynomial. And let us consider from next onwards, let us consider the polynomials over a field capital F. F may not be need not to be considered as a finite field, it may be infinite also. The theorem says that if f and g, they are the two polynomials that belong to the field f x. So, then the degree of the after summation of the two polynomials will be always less than equal to the maximum degree of f comma degree of g. A degree of f into g will be always the summation of the degree of f plus degree of g, and it can be easily proved by that sum and product of the two polynomials. So, we have not included the proof here. The next important property of the polynomials is a divisibility. So, a polynomial g that belongs to f x, which it will divide any another polynomial f which also belongs to the f x, the field f x, if and only if there exists a third polynomial called h x who belongs to the same field f x in such a way that f is equal to g into h. So, in that situation we can call that g is the divisor of f is definitely the multiplier of g, or sometimes we call that f is also divisible by g. So, if g is divisor of a, then we will write the term as g is a divisor of f like this, and if it is not, then we will write that g is not a divisor of f. Provided that f and g both belongs to the both polynomials belong to the field f x, and they are the integers in the natural set Z. Then comes the theorem of the division algorithm. Let us assume that g, which is not equal to 0, it is a polynomial over the field. Then for any other polynomial f which belongs to the same field, there exist some polynomials q and r which are also part of this f x, such a way that f is equal to my q into g plus r, where this degree of the r is always less than the degree of the g. So, earlier we were not talking about this r, we were thinking about the relation of three polynomials. F is divisible and g k is a divisor of f if there exists a third polynomial q, or earlier slide we have shown it as h. all belong to the same field. Now, we are saying that actually there may be a fourth polynomial R such a way that they can be related in this way, and provided the degree of R is less than degree of G, then this is the total division algorithm of the polynomials over the field F. And next definition, let us proceed. Suppose F G, these are the polynomials which belong to the field f x, and now not both of them are 0. Then there will be existing and another polynomial D, say if it also belongs to the field f x, and if D satisfies the following situation, that D divides both f and g. So, what I said is, suppose we are starting with two polynomials f and g which belongs to f x, not both of them are equal to 0, and there is existence of another polynomial D which is also in the field f x, and D divides both g and f, and also there is an existence of the fourth polynomial C in the same field who divides both f g as well as divides D. If this is the situation, then we will say D is the greatest common divisor of f and g, and we write it as this. If we find that the greatest common divisor of f and g or any two polynomial is equal to 1, then we will say that those two polynomials are relatively prime to each other, or we call it co-prime. We have seen actually this term co-prime when we were discussing the formation of a group. So, inside a group we have seen that if the group consists of a residual modulo p with the prime numbers modulo the numbers which are generated from the prime set with a modulo p operation, then we will see that we saw that actually any element within 0 to that p, that two elements will be always co-prime. And the co-prime fundamentals we have already discussed that time, that this is the greatest common divisor. It comes from the fundamentals of a greatest, finding out a greatest common divisor to be equal to 1 for both the polynomials. We have revisited it. Next theorem is, suppose D is the greatest common divisor of two polynomials where all these three belong to the same field. Then this D, the polynomial D, we should be able to express it in terms of dx is equal to u x into f x plus g x into v x, where this u x and v x are other two polynomial which also both of them belong to f x. This proof is very easy, and actually the greatest common divisor of D of the two polynomials can be computed by the Euclidean algorithms, and those Euclidean algorithms we will see in the next slide. We think that G is not equal to 0 for the next example, and G is not a divisor of F. D is the divisor for both of them, but G is not the divisor of F. Let us start with that example. We find that F can be written as Q into G plus R. Here we will write it as a Q1 plus R1, where the degree of the R1 is always less than the degree of G. If this is the situation, then we can form another recurring equation. G is equal to the Q1 plus R1 plus R2. Remember, in the first equation F, Q1, G, R1 all are the polynomials and all of them belong to the same field. If we can construct now G by a Q1 R1 plus R2, where Q2 and R2 also belong to the same field, these are the polynomials and they belong to the same field f x. And again going by the same way, if now R1 can be written as Q3 R2 plus R3, where actually your Q3 and your R3 both of them belong to the same field, and degree of R3 it is less than the degree of R2. So, whenever you are finding the new polynomial to form the equation, division rule, division algorithm and division equation, please remember that the degree of the newly found polynomial should be less than the degree of the polynomial immediately found immediately earlier. So, like that if I go ahead, and we will end up with a coefficients called R s minus 1 expression. All this expression q 1 to q s plus 1 and the R 1 to R s, we have told that they are all the polynomials, they should be all the polynomials that belong to the same field f x. And since this degree of the g is a finite number, so with finite number of the steps, this algorithm should, division algorithm should stop also. And if the last non-zero remainder, this R s that you are getting, it has a leading coefficient say b, then we can write that the divisor, greatest common divisor, the d, will be equal to b to the power minus 1 into R s. This step is to make this leading coefficient of d equal to 1 also, because this relation is universally true, because if you can prove that the division algorithm holds good and you can lead it and you reach to a feasible stop point, and you are able to find all the other polynomials over the field f x. So, now the polynomials u and v that we could find, which was equivalent to the last algorithm with the substitutions of R s and R s up to R 1 and into this expression that we have right now find out, we can find out actually this u and this v. Next definition, it says that a polynomial p, it will be irreducible under what situation? It will be irreducible if this p is having a positive degree, and that degree and p can be written in terms of b and c, where b and c both are the constant polynomial. We remember that the constant polynomial means the degree of those polynomials are less than equal to 0, and we will go back and revisit and check. So, the constant polynomials were defined where the degree will be less than equal to 0, and so with that understanding, if that is the situation that p is equal to b into c, where all the b and c both the polynomials are of the constant polynomial, then it is it will be true that p cannot be divided, is irreducible over that field capital F, and otherwise you could reduce it. These irreducible polynomials are of the very fundamental importance when we will discuss about the code generation through the LFSR linear feedback shift register architecture. They are actually very fundamental importance of the ring, and they can be also very fundamental concept when you will be going ahead with the discussion of the correlation analysis of the period, maximal length sequence generation, even PN sequence generation, long nonlinear sequence generation. We will see actually this expression of its importance in the generation of linear feedback shift register and also the long nonlinear sequence generation later on. The polynomials in f x, it can be written in as the products of these irreducible polynomials as in essentially unique manner. You will see it, you can verify it by some example. Now, let us come some unique factorization in f x. Suppose a polynomial f is existing over the field f x, and it is having a positive degree. So, if it is having a positive degree, I can express it in this form. What is this A? A is a polynomial which belongs to capital A belongs to capital F, and P1 to Pk, these are the distinct monic irreducible polynomials. Monic irreducible polynomials means, monic means all the coefficients of those polynomials are equal to 1, and each of these polynomials are irreducible further, and these are all the positive integer values. And if this is the situation, then this factorization is unique apart from the order in which the factors occur. So, this is called the unique factorization, the rule of unique factorization. And remember, any element b that belongs to the f, we will call that a root or 0 of the polynomial if and only if the f of b gives you equal to 0. So, to define a root of a polynomial, we have to find out actually the function, that polynomial with that value typically should raise the value equal to 0. So, now we are actually in a situation to define a polynomial f x over a field f and define its periodicity. Suppose we are having a polynomial f x and we are really interested to find the period of it. Period means it is the order of f x with the at least some least positive integer. Suppose the least positive integer here is the point of our consideration is the least positive integer here is denoted as t, such that this polynomial f x given by my x to the power t minus 1 will be denoted and we will denote this period of f which is equal to t. So, what is the meaning of that? The period is something that if t is such a number, a positive integer, such a number that so that this polynomial will be divisible by x to the power t minus 1, then we can say that the period of that polynomial is equal to t. We will test it. Suppose we have a polynomial given by x 3 plus x plus 1 and it belongs to the z 2. This is a group z 2 and it has a period 7. How will you define that it has a period 7? Because if I take up a period, if I take a polynomial as x to the power 7 plus 1, this x to the power 7 plus 1 can be expressed in form of x plus 1, x to the cube plus x plus 1 and x cube plus x square plus 1. You please continue the multiplication on the right hand side and check whether you can come back to the polynomial x to the power 7 plus 1 or not at home. And once this is the case, then we can really think that the target polynomial x to the power q plus x plus 1, definitely it is divisible by this x to the power 7 plus 1, generating these two other polynomials. So, definitely then 7 is the period of this polynomial x to the power q plus x plus 1. And but remember, if we take another polynomial who is having x to the power 5 plus x square, who is also actually having the existence over z 2, the group z 2 and the ring z 2 also, and then f x cannot be factor of this x t plus 1 for any positive integer of t. So, if you cannot find any positive integer of say t for which actually the polynomial it can be divisible, you can divide it with some constituting some polynomial with that integer value t, then we cannot find that actually that target polynomial is having any period over that. It does not have any period and there is no period, hence we declare that no period exists for that typical polynomial. For my any polynomial f x that belongs to the field f, where f is, if it is a finite field, and then f 0 which is not equal to 0, if there is a situation, then definitely there will be a period of for x. So, immediately to check if we are getting f 0 equal to 0 or not, will give you the answer whether the period exists or not. And then the second task is to find out a typical integer value t for that typical polynomial, so that you can find out the period of it. So, for example, if we can apply this formula, we apply this logic on the expression of this f x that we have seen earlier, which are actually equal to x to the power 5 plus x square. Putting the value of f equal to 0 there, we will find that the right hand side will be completely 0, which proves that actually for this polynomial we will be never be able to find any period of it. So, before searching for any period, searching for such integer which can be a period of a given polynomial, please do this checking. For another one like this f x which is equal to my x cube plus x plus 1, then in such situation we will be able to see that if I put f equal to x equal to 0 there, we are ending up with the value equal to 1. So, it proves that definitely you should search for the some positive integer for which this polynomial will be periodic polynomial, which will have a period of it, and hence actually after some searching you will be able to get this. So, with this we are ending with the Galois field mathematics and its fundamental understanding, which gives us a complete journey to understand initially the set, then the binary operation of on a set, what is the meaning of the algebraic structure of a group, then from group we learned what exactly is a ring to field, and finally, what is the meaning of the polynomial over that field. Fundamentally, we will use mostly this concept of the polynomial and the polynomials over the field for the generation of the code architecture, and for the generation of the code and the code architecture we will try to understand what are the characteristic polynomial and what is the generating function for our linear feedback shift register based codes in the next few lectures. And remember, actually with respect to the Galois field mathematics, these are the most important terms that we will be interested in context of the code generation. One is actually our characteristic polynomial, and second one will be my generating function. Remember, the characteristic polynomial is a very critical one who will generating function. This characteristic polynomial should be able to develop the generating function, where we will see later on that the characteristic polynomial actually is a divisor of some other polynomial. If it can be structured like that, if we can find out the characteristic polynomial and if it is finding out it is a divisor of some other polynomial of the LFSR structure, then the generating function can be generated, which can finally give rise to a code, say a particular code from the random sequence code generated from that LFSR structure. So, let us wait for the next 2 modules to come up, and where we will go in detail of this characteristic polynomial. We will see in detail.